Hello, and uh, Wa- Weibull distribution is very important for engineering. So, and its maximum likelihood estimator turns out to be very complicated. That's why I hope this video will help you to get this whole process a little bit more easier. And first, given a sample size n, right? X1, X2, Xn from a Weibull distribution with the probability density function. This probability density function has two parameters, beta and delta. So with this kind of form, okay. First, likelihood function. As we all know, likelihood function, because for each of xi, we have a replace this x with xi, right? And then we multiply all of them together. That's why we put this sign. This sign means what? Multiply. And the sum means summation, okay? So here, this basically just the one, each of the individual PDF for xi. You see right here, xi, replace the x with xi. Everything else would be the same. Now let's just go one step further to say, because for the constant term, right here, these two terms, they do not change with the I. Remember here we split the xi over delta as 1 over delta times xi. So xi still has to keep inside this multiplication sign, but 1 over delta could be taken out, right? Beta over delta to the power n, because each PDF has one term in it. The same thing as 1 over delta to the power beta 1 minus 1. Okay, you see this one minus 1, it becomes 1 over delta beta 1 minus 1, and then xi to the power beta minus 1. That's why we have this term and this term out of this summation sign. There's another one, is the exponential, because if we multiply exponential with the xi goes from 1 to n, because by the rule of the multiplication for exponential function, we just add all the exponents together. That's why we end up with the exponential, with the summation of those exponential terms, exponent terms. And then the only thing left inside this multiplication sign is the only thing is the xi to the power beta minus 1 right here, this term. And then of course, we could take this whole thing and then multiply to the power beta minus 1. And then why do we need to do the third step? Because the third step, we really want to put everything about xi inside an exponential. This is only for convenience, because later on we're going to take the log of the likelihood function. This is very handy, because if we take the log, everything of this one is going to be what? Exactly here. Does that make sense? How could we do that? So typically we just first we take a log of this whole thing, and then exponential. You see, think about it. This log of this guy, it becomes beta minus 1 times the summation of the log of the ln xi, and then exponential. Okay, so typically here we just do with a function of xi, right? We take the log ln, and then we exponential. basically is the same thing, right? Okay. All right. After we get the log likelihood function, then we can take the derivatives now. Here we use two formulas. This first one is the rule for ax. Remember, a here is a constant. X is the what? Is the variable. That's the rule for the math. So here, this is the derivative rule for the exponential function. Okay. And also we have the derivative rule for power function is the second one. And power function here, you gotta be careful. X is in the base. Okay. And the exponent now is the constant is m. So for example, like a derivative of x to the power 3, and then what is it? It's exactly 3 times x to the power 2, x squared, right? And then the first one, we can take a look like a derivative of 3 to the power x, and then dx. And then it becomes 3 to the power x, and then ln 3. So the difference of these two actually is obvious, because the first one is the exponential function. The variable is in the exponent part. But for the second function is what? Is the power function. The variable is in the base. Okay, that's the difference. All right. And this is the tricky part, because in the log likelihood function, right? We gotta keep this in mind. This is the one of the difference between statistics and math. Because in math, this is math, right? Remember, we always put x as what? As a variable, and the a or the Greek letters as constant. But in statistics, we are doing opposite. Here, beta and delta are what? Are variables. Not really are parameters in statistics, right? But those parameters are what? Are unknown parameters. We need to estimate them. That's why here, to take a derivative, we got to respect to beta and delta. Okay, but for those xi's, they are what? They are just sample. So we could observe them, right? We put them as constant. So here, that's the tricky part. Now think about this is the log likelihood function, right? We take the derivative with respect to beta. So this basically is like ln beta. And then take the derivative with respect to beta. That's how we get n over beta. Yes, that's the rule of the ln x dx, right? Basically 1 over x. That's the rule. And then m beta, ln beta. Here, because this kind of like a power function, that's how you get this guy. And then beta again here. So the constant term is this one. That's why we got this guy. And then minus this is a constant is gone, is 0. And then this part is exactly the what? The exponential function. Okay, so this is the base, and then the beta is on the exponent part. That's why we got you take this one, the same thing, and then log the whole thing. We got this guy. Okay. All right. And then how about we take derivative with respect to delta? So with respect to delta, the first term is no delta in it, so is 0 is gone. And then the second term, this is m beta, and then ln delta with respect to delta. That's why you got negative m beta over delta. And then this guy, there is no delta in it, right? So the whole term is gone. The only the only thing left is the last term, this term. That's how, but in terms of the delta, this is like a what? This is like a power function, because beta here you can take as what? As a constant now, because delta is the variable. So that's why we got this guy, okay? This is the derivative. And we simplify a little bit. We take the delta and the beta. Yes, some terms we can take it outside of the summation, basically like this one, okay? Because it turns out that the equation 4 is much easier, right? For example, if we let this one equals 0, right? What do we got? Because here, if we let this guy equals 0 first, we can cancel the beta. And then we multiply both sides by delta to the power beta plus 1. That's how we got negative delta to the power beta plus sum of I goes to 1 to n xi to the power beta, right? That's why we got this one equals 0. So beta delta to the power delta equals this guy, xi to the beta. That's how we got this guy here. Okay, is that correct? We just take the power of the beta to the power 1 over beta, and then here's the same thing. And then that's how you get this guy. Okay. Of course, this is I goes from 1 to n. All right. Okay. After we get the delta, right? This kind of, this is very nice. The idea is like we try to solve the equation, right? We try to use the beta to represent delta. After we get delta, right? This equation 5, we can plug in the result of equation 5 into the equation 3. Okay, that's what we're gonna do next. All right, so actually this is kind of complicated, because after we know the delta, we need to first, for example, ln delta. We need to get ln of delta, and then we need to get 1 over delta, xi over delta to the power beta, right? That's what we're gonna do next. That's exactly what. First, you see this is delta, right? Of course, delta equals the sum of xi to the beta divided by n to the power 1 over beta, right? That's exactly what we'll get for right here for delta. So if you take the ln of delta, right, ln whole thing, that's how you get this guy, right? Because it is minus n delta, that's why you got n over beta times this guy. And then here is the same thing, remember? This is exactly ln delta. And this guy is the xi over delta to the power beta. Okay, that's why you got this guy, remember? Xi beta over this guy. N. Okay, so this term. Okay, we have so many summations. Don't be scared. Actually, it turns out to be very easy. First of all, for the first 3 terms, we cannot do anything. We just copy. The only thing we can do something is the last term. Okay, the last term you can see here. this guy, this term, right? It has nothing to do with the summation anymore, because it always sum. This is what we mean by double sum, right? If you double sum, you always summed from I goes from 1 to m, then it has nothing to do with the xi anymore. That's typically we can take it out. Okay, for example, we split it into two terms, right? Xi to the power beta times Lxi. That's why we get the first one. And then the second term is negative, negative. That's how we get a positive. And then we multiply by that. The reason we can take this guy out of the summation because of what? This one is already summed. Is a what? Is a constant term. It has nothing to do with I anymore. That's why I can take it out as the denominator. Okay. And then now take a look. So this term, we just copy the fourth term, all right? And then the last term, why this one equals this guy, right? Think about this one, because this term is also a constant term. What I mean by constant here, it does not depend on I, because it's the sum. This is double sum, right? Sum, you can take it out. Remember, you take it out. If you take it out, what you left in the summation becomes xi to the beta 1 over beta. And then, of course, you can take the 1 over beta out of the xi also, right? Not just this guy. So the only thing left in the summation is just what? Xi beta on the top. And then take a look at what is the bottom. The bottom is xi to the power beta divided by n. You can see these one are the same. So basically just this guy divided by this guy divided by n. So this one gets cancelled and flipped out. So the whole thing becomes m. That's why we get this guy here. Okay. Now after you get this guy, you see how nice this one is. This is minus and this is plus. So this term, these two terms get cancelled out. Okay, we only have 3 terms left right here. Okay, this term, and then this term. Okay, now if you let this first partial derivative with respect to beta equals 0, this guy equals 0, that's how you got this guy. Okay, remember? So now finally we have equation 6 for beta and then 5 for what? For delta. Right here. This is 5 for delta. So of course these are just 2 simplified version of the first derivative with respect to beta and delta. So we should go from here. You know, this is so-called first order conditions to solve what? To get the maximized likelihood estimator. Okay. Of course, we need to solve these 2 equations. Actually, to solve these 2 equations is very complicated. Okay, this is not the purpose of this video, and I would recommend you to refer to this article here. This is the article. Okay. Yes, if you are interested in it, please go read this article. Okay, because it does not have a analytical solution, does not have a closed form solution. So it needs a more advanced method to get the solution, numerical solutions. Okay, all right. Hopefully this video will help you to understand this MLE better. precisely for Weibull distribution. And the second, this is a good way to brush up your calculus, especially for the all kinds of derivative rules, right? For all kinds of functions. All right, thanks for watching. See you next time. Bye.